Well, thank you, Josh, for making the trip from Vermont.
Yeah, my pleasure, Manuel. Thanks for having me.
Part of the paper.
Of course.
I wanted to ask you, how did you start working in artificial life as a computer scientist? We're both computer scientists.
Right.
And how did you make decisions to go where you are today?
Sure. Yeah, I guess it was not the normal path for an academic. I grew up in Canada. I went to school at McMaster University in Canada. And as an undergraduate, I discovered evolutionary robotics and evolutionary computation. So for those that aren't familiar with this idea, you have a population of solutions to a problem. Mm-hmm. In our case, usually it's a population of virtual creatures that are trying to perform some task. Some of those creatures do a slightly better job at the task than others. Those survive and reproduce. The ones that didn't do so well, the computer deletes them and repeats that process. So that had been an idea that had been around for a while. And as an undergraduate, I was just wandering around the library someday looking for something to read and stumbled across these books. Got really excited about them because this was an intersection between biology and computer science and engineering that I'd never seen before. And so I started Googling around to see, what sorts of schools and programs existed for that. And at the time, there was only one or two.
Which year would that be?
This is in 1997. So at that time, I discovered there was one graduate program, a master's program at the University of Sussex in the UK. Phil Husbands, Inman Harvey, Margaret Bowden, computer scientists, philosophers, engineers who were evolving robots. And this was the craziest and coolest idea I'd heard of. Off I went, I spent a year there in the master's program. It was and is a very unique program, a mixture of computer scientists and biologists and philosophers. And in the first half of the year, you were exposed to the other disciplines. So as a computer scientist, I was thrown into biology classes and wet labs. Wow. Biologists had to take coding classes. We were all in equal and total pain, learning the other side of the coin. And then the second part of the year, you would do an independent project on whatever. So from the beginning of my graduate career, at least, it was studying these questions that existed at the intersection of all of these disciplines. And the rest of my graduate career continued in that way. I went on to do a PhD at the University of Zurich with Rolf Pfeiffer.
Which is unusual to then continue on to continental Europe.
That's right, yeah, exactly. Continuing on to continental Europe, doing a PhD in Europe. As a North American, to go in that direction, you're kind of traveling in the opposite direction.
Absolutely.
And then I was very lucky to be able to come back across the Atlantic Ocean and spend 3 years with Hod Lipson doing a postdoc on evolutionary robotics and applying this now to hardware. Most of what I've been doing in that time was theoretical simulation work. But with Hod at Cornell, we were able to start evolving real-world machines. So that was an eye-opener for me and very exciting and led to some of our better-known work. And from there, it was on to a faculty position at the University of Vermont.
I don't know if it's something that you did in Zurich or the people that you work with in Zurich and then the work that you did in New York that somehow you revitalize this evolutionary computing, evolutionary robotics, right? You have done something that...
Oh, it wasn't just me. One of many people, I think, that, as you say, sort of revitalized that interface. So you mentioned the Gecko conferences, which is this big conference for evolutionary computation. It does bring together a lot of scientists and biologists, but it's taken a long time for those two groups to speak enough of each other's language that real science starts to emerge. I think you're right. And I still go to that conference and I still find it interesting because a lot of the interesting problems in science, they take decades, they take generations. And we live in the modern age, the cell phone age, where there's an expectation that there should be a discovery every year, things should be exponentially increasing in terms of knowledge and wisdom and information. But the hard work of science, sometimes especially at the interfaces, it takes a long time to get there. And I think accelerated by the deep learning revolution, that there is a refound appreciation for interdisciplinary work, right? That there is, in a deep network, a deep appreciation of the brain and how it works. And it took a long time to figure out how to get that to work. The perceptron's been around since the 80s, the 60s, depending on how you count. It took 30, 40 years to finally get neural networks to work properly. Same thing with evolutionary computation. How do we finally leverage the power of evolution? It produced us. It produced animals, plants, all the diversity we see on Earth. There is power there, but how to harness it is a long-term proposition for sure.
You're touching a very important point that maybe that field is living, it's winter, right?
It is still winter, absolutely.
Right, still winter for them.
Absolutely.
And then what I was surprised going over, one of the fun things of doing these chats is to really force yourself to prepare a conversation. So I know your biggest hits, but then what you do is you go through every single thing.
Oh, I apologize.
No, I have to say it was one of the easiest that I had to do. It was almost like, oh, really? Is he working on this? It's really weird, like fascinating and stuff.
Thank you.
So you're pointing out towards the fact that maybe the field as a whole, like it happened with the perceptrons during the AI winter, it didn't deliver a killer app.
Right.
And maybe what you're doing, and I want you to describe this more in depth,
Sure.
you're coming up with, and I think you're probably fighting an uphill battle in the scientific community, right? You're coming up with a killer app with showing it in robots.
That's it.
And tying it to morphology and function in a way that these purely statistical approaches, right, because now we think today in computer science, yes, we do have robots, but kind of where the big hot area is kind of this statistical thinking, right?
Correct.
And when you say, well, be careful with this statistical thinking, whether it's neural or in a way more classically statistical,
Sure.
like supervector machines. Be careful with this because none of them have a body. None of these ways of thinking, ways of learning have a body. And the body is something that evolves.
Absolutely.
And therefore you need to go back to evolutionary principles.
Absolutely.
So maybe you can say more about this new killer app that you're trying to bring into the computer science and the scientific community, that you're maybe the best and one of the first to do this.
I am definitely not the first or the last. Again, part of a wider community. I spent time in Hod Lipson's lab, Rolf Pfeiffer's lab, Dario Floriano in Lausanne in Switzerland, and many researchers working in this area of trying to take the body into account when thinking about intelligent behavior. A lot of work in robotics, a lot of good work in robotics has a killer app in a particular application, but usually that robot does one thing over and over again at high precision, right? This is the world of robotics. They're very specialized machines. But if you look at the body plans we see in nature of animals and plants, the body is designed to do many different things, to adapt to different environments. And there is an increasing focus in robotics on trying to create general purpose machines, right? A machine that can not just pick and place, but pick and place, walk from A to B, help a person, help another person, enter a disaster site, perform a large number of general purpose tasks. How do you make a machine do that? We've been trying in robotics for a long time to take a shell, to take the body and drop ever more powerful machine learning methods in there, and with the recent advances in deep learning, there's even more of that kind of thing in robotics. So myself and my colleagues are proposing this alternate approach where we don't treat the body as a shell, but a body as an enabler of intelligent action. If you don't have any fingers, it doesn't matter how sophisticated a brain you have, you're not going to be able to pick up an object. There are important aspects of morphology that matter. And thinking about fingers for lifting might seem obvious, but there are other options that are out there as well. So certain aspects of the body are not so intuitive to think about. And so when we move into those spaces about trying to design a body coupled with a statistical method to produce intelligent action, it's a very non-intuitive space for us to move in. And a lot of the traditional machine learning methods don't apply well to the body. There is no clear gradient to descend to reach the global optimum, the best solution.
Why is that? Is it because the morphological space is too vast?
It's not just too vast. So if you look at a very large neural network, that search space is very large as well. If you make a small change to one or a few synapses inside a very large neural network, If you do it appropriately, you can guarantee that you're going to make very small changes to the behavior of the neural network. And if you can make a small change to structure, and that causes a small change in function, then you have a gradient. You can march up or down gradients of behavior. If you make a slight change to an animal or a machine's body plan, you can't guarantee, or at least we don't know yet how to guarantee that it's going to have a small effect.
All right, so it's a matter of, it becomes a bit chaotic or unpredictable, the behavior of said modified organism. Therefore, the search space becomes very rugged.
It's very rugged, exactly.
Yeah.
That's right. So you can think about it this way. So if I'm doing object manipulation and I make a small change to the morphology of my fingers, maybe that has a small effect on grasping. But if I'm a walking machine and you make a small change to my mass distribution, the machine that could previously walk now falls over because it can't deal with its new mass distribution. Even if you change that mass a small amount, often that has a catastrophic effect. So we're dealing with these very rugged search spaces, these non-convex optimization problems, which are notoriously difficult for existing state-of-the-art machine methods, state-of-the-art machine learning methods to work with. So we need some other form of search. And now we're back to Gecko and the idea of evolutionary algorithms. Evolution has clearly produced a wide variety of morphologies. Mother Nature has tinkered with those body plans over time, and it wasn't catastrophic. Some cases, yes, but other cases, no. So we have an existence proof that it's possible. There is a search process. It's been running on this planet for 3.5 billion years, and it's produced a wide variety of more or less general purpose bodies with complex neural networks inside. So we know it's possible, but we haven't yet been able to replicate the full power of evolution in machines.
I was thinking when you were saying that you're completely right. I remember a few weeks ago, I think I burned one of my fingers, and it didn't even hurt. So I don't know, I put a Band-Aid on and went to sleep and woke up the next day.
Right.
And then I went to the office, and I remember I couldn't type, right? Because as I was touching, it's like, oh, okay, at the beginning it's like, oh, no big deal, I'll get used to it. But I couldn't get used to it, and I couldn't just use one hand. And that day, I couldn't work.
There you go, right?
And I said, all right, I'm gonna then print papers, and then I'm gonna make this opportunity but the problem is that even searching for the documents, it was too painful. It's like, okay, I'm gonna do it with one hand. Right. So the minimal morphological modification actually derailed my whole, whereas if I had a headache or I was a bit tired or I was hungover, let's say, I don't think it would have bothered me that much, right? It would say, all right, I can still do things that are lower level.
That's it.
Today I'm not gonna read Kant.
Fair enough.
But I can reply email on some administrative stuff.
Exactly.
So it bothered me less than the minimal. So it's a great.
There you go. So the change in morphology, it also depends on what you or the machine is trying to do. And the point is that it's very hard to predict. Structurally, it's a small change. There's just an abrasion on the skin, very localized. Structurally, it is clearly local and minor. But the impact on behavior, who knows? So it makes this an open field. So the problem of search is definitely not a solved problem when it comes to embodied designs.
This is fascinating, and it brings me to, you have 2 books out, one of them with kind of a provocative title, Designing Intelligence, Why We Need Brains. Do you think today in the AI community we're focusing too much on the statistical brain, the deep neural network, etc.?
I think so, but again, it's very hard to say what the limits are of any one approach. The current machine learning approaches are very powerful. There's been huge advances recently. So it's hard to say what the limits are. That being said, there do seem to be some limitations, 2 of them. One of them that's quite interesting is adversarial examples. It turns out to the community, somewhat surprisingly, that it's very easy to generate input that will fool a pattern recognizer, a deep learning machine. One argument why, from an embodied point of view, is because the machine can't move. If you can move, you can reorient yourself relative to the world and change your input. But if you are a passive machine, you're a neural network locked inside of a supercomputer and being fed images or video, you cannot alter the input. The input is just what you get. And if someone else has control, if the black hat has control of generating input for you, they'll always have an advantage over you. They're in a sense embodied. They can change the input that you receive. So that's a recognized limit in the field. And again, I'm biased, but I believe that embodiment is one way to help solve those problems.
So to make it a concrete example, and please tell me if I'm
Sure.
Hallucinating, right? So you see something far, and you say, "Is that my friend Josh? It looks like my friend Josh, but I don't know because Josh is not supposed to be here today.
Right.
So what I'm gonna do is and I can't go and ask. I'm shy. I can't go and ask, "Hey, are you Josh?" Because if it's Josh, it's weird, and if it's not Josh, it's even more weird.
Sure.
So what I'm gonna do is I'm gonna walk by and get very close and have a look at his face and determine if my idea is correct or incorrect,
absolutely.
Right? So you're modifying your input.
Exactly. To me, that is the easiest way to start to think about the role of the body in intelligence, is that it is a tool for changing your input. And the hypothetical example you just gave, you said, I chose to walk past my friend Josh. You chose that action, again, out of a vast space of actions you could have chosen that reduces your uncertainty. How did you know to choose that action? If you are in a different body, you have a robot that has a very different body, it's going to have very different actions available to it with which to learn about its world, to reduce uncertainty, and so on. So we can take a machine, we can take a robot, and allow it to try and come up with actions to change its input. But at a lower level, we can design the body itself, which provides different kinds of actions to the agent. So what we're really doing when we're searching the space of all possible bodies, we're searching tools with which the agent can change its input. And that space taken together provides a wider range of actions, a wider range of ways of pushing against the world and observing how the world pushes back than a single machine and its limited set of actions.
It's fascinating. I don't want to go through too much in this rabbit hole, but because given we're talking about machine behavior in the context of the article that we are writing together.
Yes.
Do you think, and I could be completely wrong, do you think that now we have these really large machines, right, that are mostly software-based or 100% software-based, let's say newsfeed, or any kind of ranking algorithm? I've done some work in understanding these algorithms.
Right.
And what you're saying, I think, even applies to them, right? That these machines, they ingest a lot of data.
That's right.
And they have this amazing processing power and learning power. And they can rank news for you. They can recommend you friends.
Sure.
They can recommend you videos. They can even create videos for you, summarizing all your list of articles that you never have time to read.
Right.
But what they can't do is they can't move. They can't somehow stop receiving this input. And whatever a movement means in that space.
That's right.
Do you think your thinking applies? A lot of problems that we're having today is that most of the information that these machines are getting in the recent time is kind of adversarial, whether we call them fake news, whether we call them monetization, right?
True.
And it seems they can't do much about it because they can't move.
They can't move.
What would it mean in that metaphor from your expertise? How would they be able to move?
It's an interesting question because the more you start thinking about embodiment or movement or changing your input, the definitions they're not as black and white as they looked before. It's not I have a body or I don't. So there's a related concept to embodiment, not my concept, it comes from the literature of empowerment, which is how much power do you have? What's the breadth of actions you have available to you? So even the most powerful learning method out there on the internet, it can choose to pay attention to a subset of the data, but it cannot generate any new data on its own, right? It can move about the internet and select different parts, but it's selecting from a predefined
or ask
whole.
for data.
or ask
Yes.
for data, right? And in which case, it may be able to collect new data. If it sends out through a crowdsourcing system, for example, I'd like to know about X, and the crowd responds with all different versions of X, then in effect, that disembodied machine has pushed against the real world and received input back. Its muscles in that case are humans or other machines that have carried out its wishes. So in that case, it is somehow embodied. And I think the important thing is not really, does it have a metal shell or not? It's how empowered is it? What is the breadth of experiences that machine can draw from the real world and learn from the data it gets back? That's, I think, the more interesting question.
That's fascinating. And in that book, are there other things like embodiment or empowerment that you think we need to start discussing when we discuss intelligence? Are there other things that, because we have a physical body in the case of living organisms, this empowerment in the case of maybe higher level abstractions, are there other things that we are not thinking about that it would be good to start discussing in the community?
Yeah, I think, I think, well, for me personally, it's the interaction between embodiment and the other aspects of AI, machine learning. So, learning, training, algorithmic bias, the social issues surrounding machine learning, that's where things start to get interesting. I think one of the intersections that's actually coming from the neuroscience literature is the relationship between the body and language. So there were some recent studies where they put human subjects in an fMRI machine and they just lie there passively listening to stories. So they're receiving language, but their motor strip lights up. So there's a deep connection between language and action. When you hear verbs, to hit, to throw, to receive, you mentally imagine yourself performing those actions, or imagine watching someone perform those actions, right? So you have a very deep connection between something that's very concrete and real, physical action, and something that's very abstract, language, mathematics. So there's a connection there, and what that connection means, why does that connection exist in us? That's missing from our machines. We have disembodied bots on the internet. We have Siri that listens to language and tries to respond to language, but Siri has no body. She has no way to experience the physical world. Siri doesn't mentally imagine what a verb means or what it feels like before producing a response to language. So we have language, but it's a very disembodied investigation at the moment. And then we have robotics, which is very embodied, very action-oriented, but the language part is missing. So there are gaps sort of between the abstract and the concrete branches of AI, I think. And there's a lot of low-hanging fruit there, a lot of interesting research questions to be tackled.
So for instance, what you're saying is that the internet might look very different if, just to go back to the example of newsfeed.
Sure.
If somehow the algorithm recommending you an article about refugees would have felt some of the pain there must be to not eat, to be cold.
Absolutely.
Right? When we read that, you say something lights up that is, oh, I can't possibly imagine what it is to be a person without home. But I remember a moment where I felt pain, and this must be 1,000,000 times more. So I want to help these people, right? And what you're saying is that connection with a sensation has ruled our evolution and animals' evolution. I mean, I don't know if other animals have language. I guess some of them have some sort of language, but we certainly have that connection.
Exactly.
And that's really impacted the way we do things. And somehow these embodied entities, we're not able to make them feel that. And it might follow a completely different intelligence trajectory.
Absolutely, absolutely. So, and by feeling or being able to imagine action, that produces or affords or creates novel associations. So if my computer sees that I'm reading a lot of articles about refugees, it might say, what else might I want to read that isn't just about refugees? It's about the human struggle, that abstract that at once abstract concept, but also very real, visceral feeling that humans have. There's a connection that we make if you're discussing with someone an event in their lives or in someone else's lives that's very painful. You will move through a semantic network that is very different, possibly very different, from more traditional computer science semantic networks like word to vec and so on, right? That we make connections between concepts through not just the physical body, but the imagined body as well. There's been great work on this in linguistics. So George Lakoff wrote a very influential book, Metaphors We Live By. And in that book, he talks about embodied metaphors. So a metaphor is a way to communicate a very abstract idea. But even abstract metaphors, a lot of them are grounded in physical experience. So
could you give me an example?
I can give you an example, which is don't look back in anger. This is an English idiom.
What would that mean?
So if you're not a native English speaker and you hear for the first time the metaphor, hey, Manuel, don't look back in anger, what would you think that idiom means?
Maybe don't regret too much things that happened.
Things that happened when?
In the past?
In the past. There's nothing in that idiom about the time or regret. I'm assuming you've never heard this idiom before.
No, never before.
So this is a great example that you were able, without me having to provide a definition to you, you were able to reason through what that very abstract idiom means because you know there's a connection somehow between back, look back, and the past. Where does that connection come from? Why do most cultures associate back with the past and forward with the future? It's because our eyes point forward in our heads. Whatever we're looking at as we move, as we walk or run through our environment traditionally, things that we see in front of us when we're looking ahead are things that are about to be in our future. Now, why that? I'm giving you sort of a just so story about why that's the case, but there are many, many more like that show that you can reason about language using the actual anatomy of the human body. And those tools are not available to a machine that doesn't have human form. It would be very difficult for a machine to reason out what don't look back in anger means without the human form.
Wow, I thought I would get that wrong actually. So I'm surprised how much
Yep.
embodied information, and I'm sure maybe all metaphors or more than half of the metaphors that we use are actually embodied in that sense.
Could be, it could be. So again, how much of the body there is in language is hard to say, but it proves that if we try and teach machines language or to find relationships between documents, we are in a sense hobbling them. We're making things more difficult for them because they don't share a common embodiment with the organisms that wrote that language in the first place.
One other thing that I think touches on embodiment is that a lot of what we do comes to avoid pain, to avoid being too cold or being too hungry or being too tired. And one would hope that our brains would have evolved and would continue evolving to avoid that. How does that relate to machines, which are entities that don't have pain, don't suffer from dehydration, they don't need to stay protected? Would that limit their development and their design?
I think that's a great question, and the evolutionary biologists talk about homeostasis, that this is a very important thing to organisms, about not being too cold, not too hot, not too hungry, not too full, to sort of stay in the middle, stay in the Goldilocks zone. And that, I think, is something that is not at the forefront of most AI researchers' minds at the moment. But it used to be. If you look at the early history of AI, going all the way back to the cyberneticians in the 50s and 60s, right, a primary focus for them was feedback. How do I mediate my interaction with the environment to stay in the middle? And I think that focus has kind of been lost recently. And it's a fascinating history to go back and read. Why was there such a focus on feedback? One of the many reasons was because they had limited computational resources. They had no computational resources. So you had to be very careful to maintain things. All machines in the 40s, 50s, and 60s, if you looked at them wrong, they would break, right? Everything was very carefully engineered. Now, unfortunately, we live in the world of big data, big compute. If a CPU craps out, we can replace it with another one.
I did that this morning.
Exactly.
Yes.
There's
Yes.
no real need to sort of maintain homeostasis, to stay in the middle. We can always add more or buy more nodes on the cloud. We can always grow. So I think that that pressure to maintain or to use intelligent action to ensure that you maintain in the middle has become less and less of a focus. And I think, unfortunately, that's a big part of intelligence that's been missed or forgotten, actually.
That's so true. So, for instance, no organism on Earth would be able to say, all right, a predator is coming, or I got bitten by a spider.
That's it, right?
I can just eat compulsively everything around me until I'm so big that this predator cannot get me, because it doesn't matter. Right. First of all, I don't have enough resources for that, and even if I did, my metabolism would not let me eat this much. So growing exponentially in size and power is not an option for me.
Right.
Therefore, evolution kicks in, right? So it's like, well, maybe I'm not going to make it myself. There'll be a version of me mutated who is immune to this venom, which will make it.
Yep.
And what you're saying is because of this expansion versus competition, we don't, these days in massive computing systems or massive AI systems such as these centralized data analysis and recommendation engines, we might not have, we're saying that we might not have enough evolutionary pressure on them to actually reach the level of sophistication that previous intelligences in nature have?
I think that's a good way of thinking about it, right? It depends on what the goal is. If the goal is to create an AI that is the best pattern recognizer out there, then maybe the way we're approaching things is sufficient. But pattern recognition for a lot of animals is not an end in itself. It's a means to an end, which is homeostasis. Mm-hmm. Survive, reproduce, make sure my children survive and reproduce and their children survive and reproduce. So there's another series of papers which tackle the question of what actually intelligence is, and this is notoriously difficult because everyone has their favorite definition. Mm-hmm. One of my favorite definitions of intelligence is keeping your future options open.
I read those papers.
Okay, right.
In physical review letters, I think they were a bunch of them.
That's right.
Fascinating.
Yeah, exactly. Which to me, I think captures the operational definition of intelligence because it has actions. Keep your options open. You have to actively do something. And you can choose what you need to do to keep your options open. And one of those is recognize friend versus foe. Pattern recognition is a part, but it is not the whole story. Right? Action is the whole story. Keep your actions open, which also brings us back to this concept of empowerment, right? How much power do you have over your environment? However, if we want to think about creating machines that keep their options open, now we've moved into a controversial area about should we create machines that keep their options open? Maybe that leads us to the Terminator scenario and Skynet and what have you. So that it may not be the direction we want to go. We may want to just make sure that our AIs are very good pattern recognizers, but that's all they do.
Even if you not let them be free and choose, a few years ago, you probably know about what we know as the AI containment problem, right? Which is, all right, so artificial intelligence is getting very good, and we think this is going to approach artificial general intelligence. So we have to contain this AI until we figure out how to make it safe, whatever that means.
Right.
So we can, containing an AI means still functional, and we are maybe using it to ask questions or input data, get predictions, but we are containing the amount of impact it can have in the real world.
Correct.
We worked with a bunch of colleagues, and we wrote a paper that's been under review forever, where what we do is we map the containment problem to the halting problem.
Oh, interesting.
Right,
okay.
So this was an insight I actually had walking on the beach with my friend Iyad, and we said, this containment problem, it looks a lot like the halting problem. The halting problem, it's a very simple problem, which is you look at a machine that you turn on and you wonder, will this machine stop operating and give me an output? Or will stay looping like when we are watching Netflix and somehow it starts loading and you wonder, is it going to stop loading and give me the movie? Or should I unplug, plug back in, and do it again? And most of the times, it's a matter of patience, right? Well, I think it's been, but there's no guarantee that either or will happen. And famously, Turing and Gödel and Church proved that that problem is actually beyond computing, beyond math in many ways, right? That in looking at a machine and determining even the most basic long-term functioning properties, it's not something that we can do as a general function. So in that paper, we very carefully elaborate that containing an AI, even if you think it's just doing pattern recognition, as soon as it's powerful enough, you will fall into the halting problem. You might think you're containing it, but you don't know if you're containing it. So yeah,
it's really interesting. I hadn't thought about it that way. That's a really good way to think about it, because it wakes us up to the reality of how difficult this problem is. It's more difficult than most of us would like to admit, like the halting problem.
Right, so as soon as you let the machine talk to you, because if you need to get something out of the machine, my background is information theory, you need some kind of channel, right? Otherwise, if it's just in a Faraday cage, well, it doesn't matter if this AI ever existed or not. But as soon as you go back to the halting problem and you don't know, will it do this to me? And as soon as you ask this question, you can map it to the general halting problem and you can solve it, right? So even this fantasy of, well, no, let's do only pattern recognition and that will be safe. No, as soon as they're powerful enough to do general computing, you go back to all the Turing scenarios that they thought about. We can't really escape the halting problem. In fact, what we argue in the paper is that this might be the first time it matters. It was a beautiful undergrad level computer science thing that you do in your final year, you prove it. Whether it was the Turing formalism or the Gödel formalism. But now that we have AIs that can actually escape and do things, now it starts to matter.
Absolutely, absolutely. And especially if we're talking about what they may or may not be able to do in the real world is a continuous space. There's an infinite number of actions that you or I can perform right now with our musculatures. It's not chess, it's not Go. There aren't a dozen moves or 100 moves. There's an uncountable number. And if it's a disembodied machine that has access to the internet, and through the internet to uncountable numbers of other people and other machines, the genie is already out of the bottle.
And the next immediate fear that we'll have is, all right, even if AIs are not evil and start manipulating us, what if there's a blackout or a terrorist attack and we lose everything in them? And then I go back to your other amazing concept that got me reading it until 3 a.m., which is the idea of embodiment for an organism has a lot of usefulness in avoiding this catastrophic forgetting and catastrophic failures. Can you talk to me a bit about that? Because I find that something that is not discussed ever when we do movies, we imagine movies or we watch dystopian scenarios or like, oh, blackout, now it's The Walking Dead. But you say, wait, there's a way of designing AIs and robots that even if you power everything down, there'll be some information that is physical that will remain.
I see. So that's right. There's this related idea to embodied cognition, which is morphological computation, that the robot can still compute with its body. So that is an idea that, again, is, when you start to think about it, it's immediately obvious. So if I am walking down the street, the moment I lift my left leg, there's more pressure on my right foot. I have communicated through different parts of my body physically without any electricity passing along the neural system up from my left leg to my spinal cord and back down to my right leg. You can communicate through the environment physically without electricity, without the internet. And animals use this all the time to communicate amongst themselves. social animals that curl up in a ball to stay warm. There's a lot of physical communication that goes on that has nothing to do with electricity. We assume, again, that we are all children of the machine age. We think that the minute the power turns out, we can stop these evil things from communicating, and whatever bad AI is happening, there's always the big red switch, something that you can shut off and stop the problem. But evolution has discovered over and over again that electricity is just one of many physical phenomena that bodies can evolve to exploit.
So you think, in a way, if we design computer systems that would exploit more of the embodied features, we might actually avoid some really bad scenarios where electricity runs out. You say there might be another way of doing them where they would still be able to provide things back to us and power up whatever we need, whether it's health systems that are preserving our life or energy systems. Do you think there will be a radical new way of designing them that even if electricity goes out, they will still, by the design, be able to keep working to some capacity?
I absolutely think there would be a way to do that. And so there are interesting scientific and engineering questions about how would we do that. But even more important are the ethical questions about should we do that. So I think our paper and others that are coming out like that are helping us to build a healthy appreciation for the power of evolution, the power of embodiment, the power of unthinking processes to unthinkingly discover interesting ways of doing things that are not the first thing that a human would think of. In some cases, that can be extremely powerful. We may be able to build resilient infrastructure that can continue operations in the face of a blackout. On the other hand, you can imagine malicious machines or unthinking machines that carry on doing the wrong thing, even if we're trying to shut off the lights for them. So I think, again, as everything in science, we need to think about how would we do it, and the why, or why not, I guess, in this case. There's a great experiment by Adrian Thompson, and this was published back in the 1990s at Gecko, the conference you mentioned, where Adrian was evolving analog circuits, and the idea was to evolve a circuit that would be able to produce a regular oscillation. It turns out that the circuit that evolved did not evolve a clock to produce a regular pattern. Instead, it evolved a radio receiver and picked up the signal being given off by a desktop sitting on a desk over there, and picked up that clock and produced an oscillatory signal. So instead of evolving a clock,
I've never heard of this, but
it's a fascinating paper, and there's a series of them. So the researchers believed, and anyone who starts reading the paper believes, oh, this is going to be cool. It's going to evolve a clock. I wonder how it's going to evolve the analog circuitry to produce a clock and produce a regular signal. It doesn't. Evolution discovers instead it's easier to evolve a radio receiver and pick up a signal from clocks elsewhere in the room. And I think, again, it's an eye-opening experiment. And this is work from the early 90s. It's been around for a long time. It shows, again, the surprising results that evolution can give us, which could be used for good, but again, it would be extraordinarily easy to use it for other things as well.
Absolutely. And I want to go next to maybe the ultimate thing that evolution has figured out, and the ultimate thing that we as humans fear and fight, which is death. I think your most fascinating paper is one where you propose that maybe mortality should be considered a feature, and if that is the case, what advantages would it have that we eventually have to die, no matter how much research in health put in, right? Mm-hmm. Because mortality might be another embodiment of something that evolution understands that is useful. And in this paper, you do a very careful calculation of what is the usefulness of dying. Right. So maybe you can describe that fascinating insight.
Sure. I mean, and again, it's not just something that I've worked on, that others have thought about this, especially in evolutionary biology. There's a huge literature on the Darwinian advantage of death. Why, if you think about evolution, it seems that one of the easiest things, one of the best thing that mutation and crossover and reproduction could give us is longer and longer lifetimes. But in some cases, in some species, that does happen. There are immortal species out there, but in the vast majority of them, mortality seems to be a feature. Otherwise, Mother Nature would have gradually evolved it out. If you've ever written any computer code, after a while, your code becomes larger and larger and more entangled, that at some point it becomes better to start over from scratch.
Absolutely.
So there's something about, the thermodynamic process of being alive and continuing to maintain homeostasis, that organisms and possibly machines as well keep coming up with more and more hacks and more add-ons and patches to keep the whole system going. And at some point it makes sense, not for the machine itself. The machine itself would love to continue forever, but the larger process that is producing these machines to build in mortality, to be able to have a halting point and start again, to work out a lot of these bugs and maybe refactor the underlying code, the underlying logic, the underlying morphology, and start again.
So once you have that insight that you actually get there through very careful simulation, that's the tool that you are probably using. What would be the next step? So you figure out that, mortality, it's a thing that...
Or it should be a thing.
It's a thing that we can't just get rid of, because I am not sure this is something that I want to get rid of. Right. And then you are really good at then doing experiments with robots that are going to say, let's see how it would play out when I do when I come up with a setup where evolution is creating some kind of death, robotic death. And how would you do that? Have you thought about it?
I guess not in reality about how you would actually do this. I mean, we could easily build in mortality to the physical machines. That's not something that I've thought about, but you definitely is probably a good idea, right? That there is a limited lifespan for these machines.
That is not right, because I think just something that you're very careful thinking is not just that when this counter hits 80, you switch off.
Right.
That there is something in the design itself.
Right. So the idea there is that there is some sort of diminishing returns. You have this system which is continuing to persist. It is trying to perform a useful task for humans, for example. It is learning over its lifetime. It is possibly changing its own shape over its lifetime. It is continuing to adapt and make sure that it can produce what it needs to. But like all things that seem to exist in this universe, the longer it goes on, the harder it is to come up with patches that you can add on to keep the system going. That there seems to be this fundamental limit, regardless of whether we're talking about machines or organisms, where the machine, or again, the system that's producing the machine, says there's some diminishing returns here. The system keeps learning and keeps adapting and keeps swapping in and out of battery, but it's not able to improve, or there is now gradual degradation. There's some sort of trade-off there where it makes sense to just start again. And where that limit is, again, it's not some hard limit like 80 years or 80 CPU cycles or what have you. It has more to do with the relationship between structure and function. It's harder and harder to change the structure to maintain function. And at that point, that's the time to start again.
And this makes me go back to your first book. You outline essentially two big questions, right? One is, how could we design systems with minimal human intervention, robotic systems? Because it's actually tied to everything we've been talking about, right? That somehow it would be a philosophical discussion probably to have in Vienna, right? If the fact that we are designing these new AI systems that have no mortality, have no pain, have no need for food, no need for shelter, if part of it comes from our deepest fears about how all those things hurt us, right? That the idea that somehow for your children you want things that you want to avoid them suffering things that you suffer. So a philosophical question would be, are we designing things that are so different from us? And precisely because of that,
Right.
like if you were a bad father, right, you would actually shelter your kid, and this is kind of the oldest story told in novels, right, that it's kind of a Greek myth that you shelter your children from things that you suffer, and precisely because you do that, it happens to them.
Sure.
Right?
Right.
Do you think that on the one hand that is it's a problem that we are designing systems this way, and going back to your book, one thing that you want to say, well, listen, let's try to remove human intervention in them. So that would be the first, one of the two big drivers of your work would be, I'm a human, I like thinking, I like doing things, but I want to get rid of human intervention to design these robotic systems and let them use only evolution.
That's it. So again, as humans trying to create intelligent machines, we view our own intelligence. And neuroscience and psychology and philosophy has clearly demonstrated that we are very flawed introspectors, right? When we try and observe ourselves thinking or performing intelligent action, that feedback loop itself is flawed. And if we are using that as a model to build our machines, we will be building the flaws into it. I wish I had never suffered those events in the past, so I will create an organism or a machine that never suffers in the way that I do, and therefore it will be happier than I am. There's half a dozen flaws in that chain of reasoning right there as one example, right? So part of the work in evolutionary robotics is to say, let's let evolution see what she can find, rather than us trying to build in our preconceptions and our biases about what an intelligent machine is. But that evolutionary process comes with a cost as well, which is somehow a loss of control. And this is, again, something we need to be very careful of when we think about this. One of my Edge articles was about exactly that. We could build three kinds of machines. We could build a machine where we say, we'd like you to pick and place these objects, and you can have 100 years and all the computers in the world to train yourself to do it. And that's probably going to be a safe machine. It'll be a useful machine, but it'll be a narrow machine. Somewhere in the middle, we might say, look, here's a number of tasks we would like you to perform, but we're not going to tell you how to do it. Let evolution find a body and brain to do it. That's somewhere in the middle, which also has some flaws as well. And at the other extreme, we could create technology that just evolves machines. The only task for the machines is to survive and reproduce. And Hollywood has shown us where that usually ends up, right? So there's a spectrum here of how much control, not so much how much control we give the machines, but how much control we give to the machines that design the machines. And where as a society we want to sit on that spectrum is an interesting ethical question to think about.
Do you think now that we are in this AI summer or spring or whatever your favorite season is,
Sure.
One of the things in this context is that AI, like wealth, but maybe even more, right? It seems to be. I think yesterday we had a new paper by DeepMind out of London that not only they're able to do from scratch solutions to Go and chess and checkers, but they now have this new algorithm that is able to do all of them at once.
Right.
Yeah, it's not general AI, of course, but
Sure.
it's getting pretty good at any game. And you can read that paper as another amazing paper by this incredibly talented group of people. And you can also read it, if you put your social science hat on, you would say, well, obviously, I was trained by Laszlo Barabasi out of Northeastern, and one of the things that you learn is, well, if you are very good at something, you have a certain fitness, and you are very connected, what happens is that eventually everyone and all the money and every talent would like to be in that node, right? And in this case, I think we've seen that DeepMind and other institutions are getting really good at doing amazing work that we all like, but also position themselves as some of a very few players that where the real forefront of AI is happening. Do you think that it's not evolution enough, right? In the sense that, right, because eventually, if we have only 10 players that are doing
Right.
AI work, I don't think your amazing models that tells you how good it would be to have 1,000, 100,000 replicas, does it worry you that? And I'm not using any
Sure.
socioeconomic analysis. I'm using actually evolutionary computing analysis.
Right. Okay, so yeah, again, I'm not a sociologist. We're kind of talking about the sociology of science, the philosophy of science, and I'm an amateur, not a professional at that. And I think it's a fascinating thing to think about. We are in a stage at the moment where there is a monoculture of certain views on how to realize increasingly intelligent machines. You can go back 10 or 20 years and maybe it wasn't homogeneous. You can go back even further and then you can see that at that time there were a very few number of people and institutions that positioned themselves as the thought leaders. And like any human endeavor, there's a lot of churn, right? There's a lot of creative churn at which there's certain periods where it seems that one or a few people finally have the answer. And if we're dealing with something like intelligence, personally, I think this is an enterprise that's going to take generations to figure out. We are at the beginning of the beginning of the beginning of the beginning. Rod Brooks and others have said this before. Let's not get ahead of ourselves. This is a really, really hard problem. And it's wonderful. In the last few years, one piece of the puzzle has clearly been solved, and we should all celebrate that and revel in it and take that puzzle piece and look at it from every possible direction we can. But I don't think we should lose sight of the fact that it is just a piece of the puzzle. It is not the whole puzzle.
And I guess one of the problems with this is that some directions are harder than others, right? So I think we have solved that piece of the puzzle by doing, right? So by investing money, by recruiting people.
Right.
One of the things about that I think is one of the concepts that even I started working on this and I read so many books. One of the things that I think is very hard for society to grapple with is that evolution is more about not doing than about doing, right? So evolution doesn't
it's very Zen
yes,
that way.
Exactly.
Yes.
So, and one can argue whether late capitalism is the opposite of Zen, right? Late capitalism it's what it has is an amazing drive, right? So it's able to marshal resources from everywhere in the world, right? From Melbourne to Seattle to Hong Kong to South Africa, and it has to put it in London. It will. Right. That's the kind of the feature that its ability to move capital at any speed possible, right? So, so it's an interesting discussion whether this kind of hyper-competitive winner-takes-all environment can actually, at some point, figure out that, well, listen, evolution has been amazing at creating us.
Right.
We are now creating other beings. Can we be zen enough so that we let things go, right? As soon as a talented student from Josh in Vermont gets any good, he's going to be snatched immediately by the guys at Google Brain in Montreal or DeepMind in London or 3 or 4, and not many more.
Right.
Right. So
and I think that is the world we live in at the moment, but it would be hard to imagine that situation will last.
That's an interesting prediction.
Forever, right? Again, we're dealing with a complex system. Maybe it's an evolutionary system, maybe it's not. But once you have centers or loci of power and everything is very centered on that and more focus goes into a more and more narrow view, that opens up new ecological niches for what's being missed by this.
Wow.
If you look at what came out of NeurIPS just this past week in Montreal, a lot more of the talks were about what are we missing? What can we not do? So even within the center of the universe of AI research, there is an appreciation that these methods have limitations. And our methods also have limitations. There's no universal answer. So then the system starts to right itself by saying, what else can we do? There were a couple of tweets that came out of the conference that said, I wonder if we had a different robot design, the deep RL algorithms would work better in a different robot design than this design. So you can see that side of the community rediscovering ideas from the other side and vice versa, right? So I think it's like most human systems, it's cyclical.
That's fascinating. And I want to finish this chat by asking you, what are you working on that is really surprising? It would surprise even that community, your own community. What are you working on these days that you have doubts about? And because I think our joint paper on machine behavior, it's kind of one of these things that we think we should study machines that way.
Right.
We have very firm ideas, but I think there is a very healthy skepticism in ourselves in this team of people who are trying to start this subfield discipline.
Right.
What things are you working on that have the same vibe that, oh, I wonder if this will become the thing that I do? Is this not? So tell me a bit about that.
Sure. So one of the things that my group is really excited about is bringing together crowdsourcing and robotics. So this comes back to some work that Iyad and others have done on this idea that maybe if we want to create truly safe AI and maybe general AI, we cannot take humans out of the loop. We can't just use humans to generate data that machines train on. They have to be part of the learning process.
Crowd sense, you use that term, right?
Crowd sense, exactly. So crowd seeding, they seed the ideas. So in the lab at the moment, we're putting together crowds of non-experts with our evolving machines through the internet, where robots are teaching humans about how to train the robots, and the humans are learning from each other about how and how. So you get these ever-increasing social and evolutionary dynamics mixing, and the idea is hopefully safe AI comes out the other end, which has brought me to you and Iyad and the other co-authors in this paper. I think safe AI is a very interesting idea because it truly finally brings in the social side of AI that's been missing in many ways since the early days. That however we go about building intelligent machines, people are going to have to be a part of that process and not just the experts. Everyone is going to have a say in how we create this kind of technology.
With that counterintuitive research idea, we can probably finish. Thanks so much, Josh,
great.
for chatting with me about these topics.
It was my pleasure. Nice chatting.
Thank you.
Thank you.